So we will do our problem sets for week 6. And let's begin with the review one. So here we have a couple of differentiations and a couple of integrations. So let's begin with the first differentiation, which involves the chain rule and the product rule. So we want to take the derivative of ln of x times sine of x cubed. Okay, so think of this as ln of one quantity, y, let's say, and the derivative of that would be 1 over that quantity. And then you need to multiply by the derivative of that quantity. And what is the derivative of x sine of x cubed? We're going to use the product rule and the chain rule. Big picture is product rule, so we have the derivative of the first, which is 1 times the second. And we have plus the first times the derivative of the second, which is cosine of x cubed times 3x squared, again by the chain rule. So this is the derivative of sine of x cubed. Let's now turn to x to the x. How do we find the derivative of x to the x? Well, we cannot use the power rule, and we cannot use the rule for differentiating the exponential function, simply because this is neither. This is not a power function. For that, you would need the exponent to be constant, and it's not an exponential function. For that, you would need the base to be constant. However, we can turn it into an exponential function by remembering that any positive number can be written as e to the ln of itself. That's just from the definition of the logarithm. Okay, the logarithm is the exponent to which you have to raise e in order to get a given number. So if you raise it to that exponent, then you get your given number, in our case, x to the x. And now what is interesting about this is that when you have an exponent inside the length, that exponent can come in front, which makes everything doable at this point. And here you can use the chain rule, and that would give you e to the x ln x times the derivative of x ln x, which is what? 1 times ln x plus x times 1 over x. You can leave this as it is. I mean, the differentiation is over. You can simplify it. The first thing is x to the x, and then you have ln of x plus 1. Okay, so that's how you can do this. And let's go to our first integration. The first integration is x cubed ln x dx. And this is a classical integration by parts. We need to think, if you like to think in terms of u and v prime. V prime in this case would be x cubed. And so equivalently, I'm acknowledging x cubed to be the derivative of x to the 4 over 4. So whether you say x cubed or you say x to the 4th over 4th derivative, that's exactly the same thing. And this is going to become x to the 4th over 4 ln x minus, and now you, according to the formula of integration by parts, you need to take the derivative of ln x. Okay, so I mean, we should all remember that the formula of integration by parts is the integral of f prime g is fg minus the integral of fg prime, which is exactly what we just applied. Right, let's finish this off. So this will be x to the 4 over 4 times ln x minus x to the 4 over 4 times 1 over x dx, which is x to the 4 over 4 times ln x minus x cubed over 4 dx. And the antiderivative of x to the 3rd is x to the 4 over 4, so we get two denominators equal to 4 multiplied with each other, which will give us x to the 4 over 16 plus c. And that's it. And as for the last one is the integral of, oops, again, Zoom is a little acting up here with the recording, but do not worry. Everything is under control, or it will come under control. So we want the integral of cotangent of x dx, and this is a classical substitution. So cotangent is what? It's cosine over sine. And we said u is equal to sine x, and du will be cosine x dx, which means right on the top you have everything that you need. So this is your du. So this will be du over u, which is ln of absolute value of u plus c, and that's ln of absolute value of sine x plus c, and that's it. Okay, let's now turn to our regular multivariable stuff. So today we're discussing directional derivatives and the gradient. And we have the function f of xy to be equal to ln of x squared. I'm sorry, it's y squared minus x cubed. And we want to find the directional derivative in the direction of the vector 1 over square root of 2 negative 1 over square root of 2 of the function f at the point 2, 3. Okay, so in particular, this directional derivative is equal to what? It's equal to the gradient of f at 2, 3 dot with the given vector. That's what we need to compute, okay? Well, obviously the only thing that we really need to compute here is the gradient. And the gradient, I remind you, is a vector whose components are the partial derivatives at a given point. So let's find the derivative with respect to x. So that will be 1 over y squared minus x cubed times negative 3x squared. And this means that f sub x of 2, 3 is negative 12, and f sub y is equal to 1 over y squared minus x3, x cubed, I'm sorry, times 2y. And f sub y at 2, 3 is equal to 6. Okay, so basically our directional derivative of f at 2, 3 is the gradient, which is the vector negative 12, 6, dot with the vector 1 over square root of 2, negative 1 over square root of 2. This directional derivatives gives us the rate of change of the function in the direction of that vector. So we will have minus 12 minus 6, that's negative 18, divided by square root of 2. I mean, you can simplify this if you want. It's not necessary. You can write it as negative 9 square root of 2 if you write 2 as square root of 2 squared. But, you know, again, either answer is perfectly fine. The next question is to start with a function f of xy equal to sine of x plus y squared, and compute the rate of change in the direction of fastest increase. At which point? at pi comma square root of pi. Okay, so in general, we know that what we're after here is simply the magnitude of the gradient. The magnitude of the gradient is precisely the rate of change in the direction of fastest increase, which is the direction of the gradient. Assuming that the gradient, of course, is non-zero, if the gradient is zero, then all the rates of change are equal to zero. So this is what we want to compute. So to compute this, we will have to first find the partial derivative. So this is cosine of x plus y squared. And f sub x at pi comma square root of pi is going to be cosine of pi plus square root of pi all squared. So cosine of 2 pi, same as cosine of 0, which is 1. And f sub y, here the chain rule becomes a little more pronounced. So it's x plus y squared times 2y. And f sub y of pi comma square root of pi is equal to cosine of pi plus square root of pi all squared, same as before. Only this time we multiply by 2 square root of pi, which of course is going to give us, since we already know that the first component is 1, is going to give us 2 square root of pi. So the gradient is simply the vector 1 comma 2 square root of pi. And the magnitude of the gradient, which is what we're after here, because that's exactly the rate of change in the direction of the gradient, or more precisely, the direction of the normalization of the gradient, is square root of 1 squared plus 2 square root of pi all squared. You can slightly simplify this. This is 1 plus 4 pi, and that's it. Okay, and the last problem. For the last problem, we start with the function f of xy to be x squared times y, and we're going to find all the unit vectors in the direction of which the rate of change at the point 1 comma negative 1 is 0. Let's write this so that we can digest what the answer is asking, what the problem is asking for. So determine all unit vectors. That usually entails a normalization in the direction of which the rate of change at 1 comma negative 1 is 0. So imagine that you have such a vector. So let's say that this is a unit vector AB, and ask yourself, what is the rate of change in the direction of this vector AB? So by saying that it's unit, we have that a squared plus b squared is equal to 1. But let's ask what the directional derivative, meaning the rate of change in the direction of this vector, is at the point 1 negative 1. For that, we need the gradient of the function. And what is the gradient at 1 negative 1? Well, the derivative with respect to x is 2xy. So this gives you negative 2. And the derivative with respect to y is x squared. So that gives you 1. So that's the gradient at that point. So the rate of change now, which is the directional derivative, that's what the directional derivative is, will be the dot product of the gradient with a specific unit vector. So that is going to be -2, 1, dot AB, and this is -2A plus B. So pretty much what you want here is this rate of change to be equal to 0. That's what we asked for. So you want -2A plus B to be equal to 0, which means that B is equal to 2A. Okay, so now the question is, how do you find odd numbers A, B so that A squared plus B squared is equal to 1 and B is equal to 2A? I mean, there are different ways of doing this. If we want to proceed along the most simple-minded way of solving this, then if we don't want to do normalization, as I mentioned before, then all you can do is take this and plug it into, the first equation. So that will give you A squared plus 2A all squared is equal to 1, which means that A squared plus 4A squared is equal to 1, which means that 5A squared is equal to 1, which means that A squared is equal to 1/5, which means that A is equal to plus or minus 1 over square root of 5. And so B will be plus or minus 2 over square root of 5. And now we can put together our two vectors, so the two unit vectors for which the rate of change in their direction is 0 are going to be 1 over square root of 5, comma 2 square root of 5, and -1 over square root of 5 minus 2 over square root of 5. So in the direction of these two vectors, the rate of change is equal to 0, and we found exactly what we wanted. Thank you so much for watching.